In this final talk on effect modification, I'm going to talk about using case control study data to assess effect modification. I'm going to talk about comparing additive and multiplicative effect modification using a continuous scale, and also why it is that additive effect modification is really the most important measure in public health terms. So let's start with case control study data. Now, the problem with using case control study data to assess additive effect modification is that we can't calculate incidence rates or prevalence rates, for that matter, from case control study data. And the reason for that is because we artificially set the case and control ratios and numbers of cases, numbers of controls. And that means we simply just cannot get incidence or prevalence measures from the case control study. So we may want to get a measure of additive effect modification. So the reason I showed you the method of getting assessing additive effect modification on a relative risk scale is because it can be applied directly to case control studies, because we would treat the odds ratio as an estimate of the relative risk. So the odds ratio is on a multiplicative scale. So let's look at these data, and this is for a case control study. So we have here the situation as I showed you before, very similar to the alcohol and cigarette smoking example, but instead of cumulative incidence ratios here in this table, we have odds ratios. So we have the odds ratio for the health outcome in the group which is not exposed to A and is not exposed to Z. So that's the baseline group. So the odds ratio is 1 by definition. And then of course over here in the other diagonal corner we have the odds ratio for the combined exposure to A and Z, which is 7. And here we have the exposure for Z alone, and here we have the exposure for A alone. And we can set these data out in the form of these blocks. Similar concept to the tables that I showed you in my previous talk. And you can see that each of these represents one of these cells, plus this one here is the expected as opposed to the observed, which is this one. But let's go through them. So you can see that all of them have a baseline. As I said before, even if everybody is not exposed to A or Z, there is some rate of the health outcome occurring. And that is the same, this baseline occurs across all of these cells. So the 1 is the baseline, which A and Z add to. So here you can see illustrated, we have the baseline, and then the additional risk attributable to A is this amount here. And here Z, this is the attributable amount for Z exposure. And here would be the expected, if based just adding these two blocks, leaving one baseline, adding Z to A, and this is what we'd expect. This is our expected level. But in actual practice, in actual fact, when we carry out our study, we get an odds ratio of 7, and that represents this extra amount, an extra odds ratio amount of 3 on top of what we'd expect, including the baseline. So this is just another way of assessing additive effect modification on a multiplicative scale. And so it's exactly the same as the previous example using cumulative incidence ratios. Okay, let's move on to looking at things on a continuous scale. And so for the sake of this example, we have lung cancer incidence rate on the vertical axis, and we have the number of cigarettes per day on the horizontal axis, and as you would expect, represented by this yellow line, the lung cancer incidence rate increases as the number of cigarettes per day increases. And then we have a second exposure, which I should call A, but it could be something like asbestos or radon, both of which act together with cigarette smoking. And this second exposure A, it adds one additional unit of lung cancer risk increase. But it doesn't matter what we assume here a constant exposure to A, because we have no scale of exposure to A. So we'll assume a constant exposure to A, but you can see as the number of cigarettes per day increases and the risk directly attributable to smoking goes up, it only adds exactly the same amount, one incidence rate unit of extra risk on top. It doesn't matter what level of cigarette smoking. So we can say that it's acting additively with cigarettes. So, okay, let's move on. And here we have a situation where the exposure A, it's in a different scenario, and it's acting multiplicatively. So here we would have a relative risk at no cigarettes per day of 2. It was 2 divided by 1. The incidence 2 divided by the incidence 1. And so as the risk from smoking goes up, the exposure A, which is constant, continually doubles the risk, the incidence rate from the smoking. So we continue to have, at any point on the scale, a relative risk of 2. It's always 2. So there's a constant relative difference, or 2 times, as opposed to a constant absolute difference under this scenario here. These are both alternative scenarios where A is acting multiplicatively with cigarette smoking, and in the other scenario, A is acting additively with cigarette smoking. Now, if you remember, as I said in an earlier talk, effect modification represents a departure from the expected on the scale that you're examining. So these two lines here, the orange line on the multiplicative scale is the expected, and on the additive scale, this would be the expected. So depending on which scale you're looking at, neither of these two represent effect modification. So on an additive scale, this is not effect modification. However, if you were looking at this line on a multiplicative scale, additive scale, it is definitely effect modification because it is a departure from this line. On the other hand, if you're examining the situation from a multiplicative scale perspective, this line is not effect modification, but this line here would be. This is effect modification. In fact, it would represent antagonism on a multiplicative scale, whereas this line would represent synergy on an additive scale. So it is departure from the scale that you happen to be examining at the time. So, and here we have another situation which we can compare with the additive and the multiplicative scenarios. So we have this, if we find that exposure A in fact causes this situation, so it's less than a constant relative risk of 2. As we go up here, this is the ratio of this to cigarettes becomes increasingly less and less. So on a multiplicative scale, this represents antagonism. However, if we look at this line, this dashed line on an additive scale, because it's also a departure from the expected, but it represents synergy. So this is synergy on an additive scale and antagonism on a multiplicative scale. So this really illustrates clearly, I think, how important it is to express effect modification, synergy or antagonism in relation to a particular scale. And the next slide really largely sums up what I've just been saying. Synergy on an additive scale can mean no effect modification on a multiplicative scale. In other words, the multiplicative line, the orange line here, is no effect modification on a multiplicative scale, but it is synergy on an additive scale, represented by this line. And antagonism on a multiplicative scale can be no effect modification on an additive scale. So represented by this line here, which is no effect modification on an additive scale, but it is antagonism on a multiplicative scale. And finally, synergy on an additive scale can be antagonism on a multiplicative scale. So this represented by this dashed line here. So this slide simply just sums up those three situations. So in the examples that I've been showing you to do with effect modification, we've used factors that interacted but which were both causal. And this becomes more complicated to carry out these sorts of analyses if you've got preventive factors, which, in other words, which reduce the risk. So the easiest way to deal with that is to examine it in terms of the lack of the preventive factor. So that then becomes a risk factor or causal factor. And so then you can do these diagrams and carry out these analyses of effect modification a lot more easily. So that would be my advice. Use the lack of the preventive factor, and an example of that would be the absence of vaccination rather than vaccination itself. Now, as I've previously said, the thing that's most important in public health is effect modification on additive scale. In other words, it's departure from expected additivity of effects that's considered to be most important. And to some extent we illustrated this when we used that example comparing lung cancer and heart disease in relation to smoking, where we showed that even though lung cancer had a much greater relative risk than cardiovascular disease, nonetheless the absolute effect was much greater with cardiovascular disease. So that was looking at it on an additive scale as opposed to comparing relative risks for lung cancer and cardiovascular disease on a multiplicative scale. So it's the departure from an additive scale which is most important, and that's why we really need to understand how to use case control study data to assess additive effect modification. So the thing is that we often, in epidemiology, we assess effect modification on a multiplicative scale, and we say, oh, well, there's no evidence of multiplicative effect modification, but in fact that doesn't really mean there's nothing of public health importance, because if we're simply observing the expected value on a multiplicative scale, then that could be quite a lot of additional risk. So that's why it's important to assess things on an additive scale, not just a multiplicative scale. And I use this example here of lung cancer in relation to cigarette smoking and asbestos exposure to illustrate this point. So again, we set out some relative risks here for lung cancer. So in relation to asbestos exposure and cigarette smoking. So these are all relative risks, and so again we have our baseline, which of course by definition is 1 in people who are neither smokers nor asbestos exposed. And then of course we have here people who are both asbestos exposed and smokers. So if we assess effect modification, first of all on a multiplicative scale, we would multiply these two values here together. So for the value for smoking, the odds ratio for smoking, and the odds ratio for asbestos exposure in non-smokers. We multiply the two together and we get 50, which is exactly the same as the observed relative risk. So we would say, if we were simply assessing things on a multiplicative scale, then there's no effect modification, no interaction between the two. On the other hand, if we went to an additive scale, and if you remember, we would add 10 to 5, and then we'd subtract one baseline, or 1, and we get 14. And so that is our expected, given the separate effects of smoking and asbestos exposure. We compare that with our observed relative risk of 50, and you can see that there's a very great deal of effect modification occurring on an additive scale. So this simply illustrates the importance of focusing on the additive scale in terms of assessing public health importance of effect modification. Before I close, I want to just mention very briefly the area of gene-environment interaction. This is quite a big area these days, and many of my colleagues here in the School of Public Health are working on this. It's also sometimes referred to as molecular epidemiology. So this is where we examine how different genetic variants, in particular genes, interact with different exposures. For example, some people with certain genetic makeups may be far more susceptible to the effects of cigarette smoking than people with other genetic variants. So I mention this because it's a big area, and some of you may have already worked in it, or some of you may be getting into it. But my main point is that, of course, this is an area where we're examining, all the time we're examining effect modification. So here we come to my final slide, where I try and sum up the key points. And the first one is that effect modification is not something to be avoided. It's a real effect, and it's something we should in some ways embrace and study it and see what it means. And in that sense, it's completely different to confounding, which is a nuisance. And so we use the various methods that we've talked about to try and get rid of confounding from our data, eliminate as far as possible. But we definitely don't need to do that with effect modification. Second thing to remember is that there is a difference between biological and statistical interaction, or effect modification. And in epidemiology, we're mainly measuring statistical interaction, but that is in some way reflecting something biological or something mechanistic going on, and we might want to explore that further. It may give us some important insights into mechanism of effect, it may give us some insight into the most cost-effective intervention measures. The third point is to remember that looked at statistically, effect modification is scale dependent. So never talk about effect modification or synergy or antagonism without actually mentioning which scale you're referring to, whether it be the multiplicative or the additive. And also remember that it's departure from additivity that implies the biological interaction and potential public health importance. And that's important to remember because when we carry out the comparison of strata method, or if you go on in epidemiology and you use logistic regression analysis, that really does focus on assessment of multiplicative interaction. And so just because we don't find the evidence of multiplicative interaction doesn't mean that there's nothing of public health importance going on. So always keep that in the back of your mind. We combine strata because we're looking to detect causal factors or preventive factors for various health outcomes. But if we want to take it past that level and we want to assess the degree of public health impact of a particular exposure, then we really need to kind of move into looking at the data from an additive perspective. So finally, I want to reiterate that this is a difficult concept, effect modification, and many experienced epidemiologists still have difficulty with it. I've tried to make this tried to break this lecture down into various steps and make it as comprehensible as I possibly can. But there's no doubt about it that if you go over it several times, I suspect you'll get an increasing amount out of it. It will make more and more sense. And it's like epidemiology as a whole. We teach it in a linear fashion, but it can't really be understood in a linear way. And the best thing to do is to recycle through all of the talks several times probably. And each time you do that, then things will fall into place more and more. and I think that'd be particularly the case with effect modification. So good luck with that, and remember, I'm always available for questions or things you don't understand, so feel free to email me. I seem to be most responsive to email.